Hey Chem Kids, Campbell here. In our video on Chapter 20, we're going to talk about electrochemistry and electrochemical cells. Now, what is an electrochemical cell? Well, it's a device that uses an oxidation reduction reaction either to produce electricity or requires electricity to operate. So like recharging a battery, you're using electricity to reverse that process. Or electroplating, but we'll talk about what that is later. Now, there are two different types of electrochemical cell. There's Voltaic cells, or galvanic cells, which are batteries. They use chemical energy to generate electricity. So that is actually a Voltaic cell. There are electrolytic cells, and those use electrical energy to produce chemical energy. So like I said, that's like the recharging the battery. That's an electrolytic cell. Now, let's look in a little more detail about what's going on inside of a voltaic cell. So in a voltaic cell, we have oxidation reduction reactions going on, but we have to keep them separate. So we need to keep, for example, with the zinc reaction, we have zinc, it's actually going to become zinc plus 2, happening in one chamber, and then the copper reaction happening in the other chamber. So we have to keep them separate because what we want to do is we want to harness the electricity or the transfer of electrons. And so these two things, these reactions, are connected by a wire so that the electrons can transfer from one to the other. And then I can harness it to make electricity. Right? Electricity is the flow of electrons. Now, I also have to have this thing called a salt bridge in here. The salt bridge here just connects the two containers together, and it allows the ions that are building up to flow from one chamber to another, and that allows it to keep charge balance. So I can keep electrons flowing into one, and so I have like a total loop here of stuff going on, of transfer of ions. So that allows this reaction to keep going. Otherwise, the reaction would eventually stop. Now, let's take a look at that reaction. It's a zinc-copper reaction. And so what's going on here, the overall reaction going on is I have zinc reacting with copper plus 2 to produce zinc plus 2 and copper. But you see that they're not actually happening in the same place. So really what's happening is I have zinc that's becoming zinc plus 2, right? It's becoming oxidized because I'm losing electrons. Lose electrons, oxidize. And copper here is going from plus 2 to solid copper. So I am being reduced, right? I am reducing my charge. I am gaining electrons. And in fact, if you look at the picture, kind of a blow-up image of what's going on here, zinc is actually kind of like dissolving. I'm losing zinc ion into the solution so that electrons can flow from the zinc all the way over here into the copper. And when the electrons deposit in the copper, right, that means a copper plus 2 ion is going to come out of solution and deposit. So what's really happening here, this is what would happen if we watched this after a while. The zinc would be getting smaller and smaller as it came apart and became zinc ion. And the copper, we're actually making some copper, solid copper, by depositing copper onto the wire. And if you remember, in first semester, we actually did that. Remember, we deposited copper onto a wire? It's pretty cool. It was in one of our chemical reaction labs. Now, really, we should write these equations as half reactions because that's really, right, they're happening in isolation. So we have zinc becoming zinc plus 2 and losing 2 electrons, and the copper going from plus 2, gaining 2 electrons and becoming copper solid. So we write them as half reactions because we're keeping them separate. Now, there's some terminology you need to know, and one is that the oxidation here is being done by the zinc, right? It's the one that's losing electrons. We call the thing that's undergoing oxidation the anode. So in this case, the zinc is my anode. And reduction is occurring at my cathode. That's the thing that's gaining the electrons. Now, how do you remember that? Well, I call that red cat, right? Red cat. Reduction occurs at the cathode, which means that oxidation must occur at the anode. And electrons will flow, right, from anode to cathode because the anode is oxidized, losing electrons. The cathode is reduced, it's gaining electrons. Those are some things you need to remember. Now, there are two ways to write these equations, and you'll see them both ways, and that's why I wanted to put them out there like this. There's the overall reaction, which you saw on the last slide, the zinc solid plus copper plus 2 ion yields zinc plus 2 plus solid copper. That would be a normal reaction equation, but sometimes you see that equation abbreviated into kind of half-cell equations without arrows. So instead of arrows or pluses, we have little slashes. So here we have zinc. We're starting with zinc, and we're forming zinc plus 2. So I separate that by a little dash, and then that's being separated, so double dashes, by copper plus 2, which is becoming copper. So it's two ways of writing this reaction equation. The second one shows it as like the half cell. Now, how does a voltaic cell work? Well, for a voltaic cell, in order to take chemical energy and make electrical energy, this has to be a spontaneous reaction. When you put a battery into a device, you need it to turn on, right? You need electricity to start right away. So if it's a voltaic cell, then this is a spontaneous reaction. And in order to have that happen, I need a metal that's willing to give up its electrons, willing to give away those electrons, and another that's just wanting those electrons. So I need something that likes to be oxidized with something that likes to be reduced. And we can calculate that, and we're actually going to learn how to do the calculation in class, but it's called the standard cell potential, or the E cell. And it's really a measure of the spontaneity of this reaction. The units of the E cell is the volt. And like I said, in volts, right? 1.5 volt battery, 9 volt battery. And so that's the unit. But the standard cell potential, we will learn to calculate in class. But you need to know what it is. And you need to know that if the number we get is greater than 0, so a positive number, then the reaction is spontaneous, and it's going to happen. Now, let's talk about the different types of voltaic cells. Of course, we have what are called the dry cell batteries. So the typical batteries that you're used to putting in your calculator and your flashlights and your smoke detectors. And here, the electrolyte solution, it's not really a liquid. That's why it's called dry. It's actually a paste. And a typical battery has a zinc anode, so that's the oxidation. But the cathode is more complicated. It's a manganese oxide. Not that you need to know that, but you need to know that a dry cell battery is a type of voltaic cell. Another type of voltaic cell is a lithium-ion battery. We've heard a lot about lithium-ion batteries lately, right, with the hoverboards. In that case, the oxidation is lithium, and again, the cathode, there's manganese oxide in that cathode again, just a little different than our dry cell battery. So, dry cell batteries, lithium-ion batteries, and my third type is called a fuel cell. In a fuel cell, it's actually a reaction with hydrogen and oxygen. So hydrogen is actually being oxidized, hydrogen gas is being oxidized, and oxygen is being reduced to produce water. So this is a great battery because, hey, if you're making water, that's a good thing, right? This is environmentally friendly. So those are the three types of voltaic cells. Now, rechargeable batteries are both. Rechargeable batteries are voltaic cells, but they're also electrolytic cells. A good example of that is a lead-acid battery or lead storage battery, like the batteries in your car, right? It's a voltaic cell when it's starting your engine, right? You need that battery to start your engine. If the battery's dead, right, your car doesn't start. But while your car is running, it becomes an electrolytic cell, and your car starts to recharge that battery. Pretty cool, huh? So lead-acid battery is both voltaic and electrolytic. Goes both ways. Now, let's talk about the electrolytic stuff, which is called, we can talk about electrolysis. Electrolysis reactions are actually non-spontaneous oxidation reduction reactions. So if we did a calculation of the standard cell potential, we would get a negative number. That's why they require electrical energy. So I have to put in energy in order to make this happen because it's not spontaneous, right? It's like you cleaning your room. That's non-spontaneous. We got to put some energy in to make that happen. Same thing with electrolysis. Some good examples of electrolysis. I'm in the way again. Electrolysis is electroplating. So when they plate silver onto other metals, because silver is really expensive, so if you just plate it onto the surface, they actually use electrolysis to do that. You get a nice thin film of silver, which is pretty. Another type of electrolysis is water. You can actually make hydrogen and oxygen gas by putting electricity through water. So if you take water, right, put electricity through. Non-spontaneous reaction. Remember, we talked about that when we were talking about spontaneity. If water spontaneously made hydrogen and oxygen, that would be a very explosive environment. But we can do it. We just got to put electricity in. All right, so that's all I got for you in this video. In class, we're going to learn how to calculate those E cells. So I'll see you in a bit.